Hi, welcome to today's school seminar and hope you are doing all well. And please give a warm welcome to Dr. Faheem Ullah, who is a research fellow at the University of Adelaide and a member of Center of Research on Engineering Software Technology Groups. Faheem research focuses on implementing and evaluating big data analysis frameworks and big data storage solutions and developing software treat models. And the topics of Fahim's talks is evaluation of big data system in edge and cloud environments. Please, if you may share your screen.
Sure. Can you see my screen, Anita?
Yes, everything's perfect.
Okay, great. Uh, Thank you, Anita, for the introduction and for giving the opportunity to present our work. Hello, everyone, and good morning. As Anita mentioned, I'm Faheem, and I am a postdoctoral research fellow at CRIST, Center for Research on Engineering Software Technologies. And in today's talk, I will discuss about our work related to big data systems in edge and cloud environment. More specifically, I will first introduce the topic for the benefit of the audience, that what exactly is the key concepts around big data, cloud, and edge. Then I will focus on the work that we do in that area in our research center. Then I'll present a couple of our projects and their findings. And then moving on, I will talk about some of the future trends in big data, what we can look forward in this area in the next, let's say, 5 to 10 years. And finally, I will finish the talk with some more concrete research questions that we can focus on answering in the near future. So briefly introducing our big data clusters. So essentially in our research center, CRIST, we have 5 different clusters. I am part of the big data research cluster, which is certainly led by Professor Ali Babar. In this cluster, we are 3 postdocs and 3 research engineers, and we have 1 PhD student. So the work that I'm going to present, it is primarily the work of this cluster. So starting with the very basic question that what exactly is big data? So normally we do get this question like, because the name itself refers to some kind of, the first thing that comes in our mind is the size, that someone can ask us that whether a terabyte of data, is that big data or not? So essentially there is no such crisp definition of data that, okay, this is a threshold. If the data is beyond that size, it would be called big data, otherwise it would not be called big data. There is essentially 2 papers written on this very topic, that how to define big data. And many of the researchers, they agree that there is no crisp boundary. That is why we define big data in terms of its characteristics, that what exactly are the key aspects or attributes of big data. So essentially the way it is that it is the kind of the high volume, high velocity, and high variety of information that we can collect for some kind of enhanced processing and extracting insight. So the 5, some people associate big data with 3 characteristics. The recent works, they bring 2 more, and they call 5 V's of big data. Probably majority of you guys would be aware of it. I would just briefly touch upon these and then move forward. So the first one is certainly the volume, that it should be large in size. The next one is the variety, that it is in different formats. So it is structured, it can be unstructured, it can be semi-structured data. And the third one is value. So we should be able to extract some useful insight from the data. If we have very large size data, but we can't extract any meaning out of it, anything useful for us, we may not be able to term it big data. Another one is the velocity. So that is another important aspect, that it should be generated at a high speed. So let's say if we collect a terabyte of data over the span of 5 years, probably we may not be able to call it big data. So it should be generated at a high speed. And the last one is veracity, which means that it should be, the quality of the data should be good enough. It should have not many missing values. It should not be kind of confusing data. And on the other hand, it should also be trustworthy data, because if we have very inconsistent, uncertain data, uh, instead of giving us some insight, it may confuse us if we analyze that data. So these are the 5 basic characteristics of big data. So the next question is that why big data analytics? So we probably hear a lot about the boom of data. So probably at this time we produce the largest amount of data ever humans have produced. I'm talking about the digital data, because more and more things are getting digital. And because of that, if we have data, there is a very common saying that data is the new oil, which means that the more data we have, the more we analyze it, the more value we can get, and the more beneficial we would be if we talk in terms of some businesses. So this graph shows some of the global big data market, that how much investment is being done uh, in in the area of big data, being that in the development side, being that in the from the business perspective, that major organizations, they are incorporating big data analytics in order to give them some kind of competitive advantage. So starting from 2011, this graph shows that by 2027, we would have around $103 billion market for the big data technologies. And we can see a consistent increase, that people are realizing the importance of big data analytics, and that is why they're investing more and more in this area. And why they are investing, what is the essential benefits? So there are so many domains where big data analytics is making its mark. For example, in the healthcare domain, a lot of data is produced in different forms. For example, in terms of images, in terms of scans, in terms of the applications, the healthcare, e-healthcare applications, they produce a lot of data. And then the data is collected and analyzed for various purposes, like, for example, for prediction of a disease, or for diagnostics, or for active healthcare. Similarly, in the case of entertainment industry, big data analytics are quite widely used, because the data that is generated in the entertainment industry, that is quite huge. Like, for example, according to one statistics, around 300 hours of data or videos is uploaded to YouTube per minute. And that data, if analyzed for different purposes, like, for example, understanding customers' preferences and so on, so it can give a lot of benefit to the to different businesses. For example, according to one statistic, Netflix saves around $1 billion using big data analytics to understand user preferences and accordingly offer the services. Same is the case with, like, in security, primarily in cybersecurity, we see a lot of usage of big data in order to uh, collect the network traffic in real time, and then give us the security landscape of our organization, that okay, where we are at risk, whether some attack is happening, whether some kind of malicious activity is going on. So those kind of things can be detected in almost real time with the help of big data analytics. So it's the case we see its usage in oil and gas and smart cities. Uh, this slide presents a very abstract level view of what a big data ecosystem looks like. So when we talk about a big data system, it is a combination of a few layers. So starting from the very bottom, we have the resources distribution. So here comes the hardware layer. We have a cluster, we have the network among which connect these different nodes in the cluster, and then we have different kind of devices. For example, we can have a high-end server, we can have a laptop, we can have some kind of Raspberry Pis. So those things comes at the very bottom layer. Then on the top of that, comes the resources type. For example, the kind of storage that we use, whether we use SSD, whether we use HD, or some kind of storage devices. Then also the flavors, like for example, we use very large size virtual machines, very small size virtual machines. On the top of that comes the big data technologies, like for example, Hadoop, Cassandra, Kafka, and so on. So essentially, what these technologies do is that they distribute the storage and processing of data among these computing nodes, and they try to make optimal use of these underlying resources. On the very top layer is the first is, of course, the application where we want to apply a big data system. So as I mentioned in the previous slide, that there are a variety of application domains like entertainment, oil and gas, and so on. So depending upon our requirements, we can accordingly use a big data system. Then as for the data generation is concerned, so we have different kinds of data for which big data systems are used. Like for example, we could have very well structured tabular format data. We could have semi-structured data, or we can have unstructured data in the form of videos or images. Then the sources of data, that where from this data is coming, they also vary, and there are a variety of sources available. For example, it could be some kind of IoT sensors. It is social media is another very big source of data. There could be some kind of databases or users' mobile phones and stuff which can generate a lot of data. Another important aspect with this, with regards to data generation, is its access pattern. So some of the data we use it quite kind of it's normal access. Another one is like for in longer terms we access that data. And associated with the access pattern is the lifetime of the data. So sometimes data, it is hot, it is warm. Like for example, if we look at something that we upload today, let's say to a social media, to Twitter or to Facebook or on photos, so that is more frequently accessed. People kind of like it or see it. But if we see some data that we have uploaded to some social media account, let's say 5 years ago, so that would be sitting in a cold or a very cold area. So the way this data is placed in the databases, it is also kind of optimized based on how frequently the data is accessed and when the data is more likely to be used. And the last aspect is about the data processing type. So over there, we have primarily two types of processing types, which is the first one is the real time, where we want to analyze and process the data as soon as it is produced. And another one is batch, where we establish a particular window that, okay, I will collect the data for, let's say, one day, and then when it is collected as a whole, then I will process or analyze the data for extracting some kind of insight. So uh, that also depends upon the user, that which kind of analytics he requires. And lastly is the analytics, that what kind of analysis we do in terms for with respect to these big data analytics. So we use optimization algorithms, like for example, finding optimal or near optimal, like in terms of the searching algorithms. So sometimes those optimization algorithms, they could be computationally quite heavy, and the data size could also be very large. So in that case, we make use of big data analytics to reduce the time to reach that optimal or near optimal value. And of course, AI is another very kind of dominant topic with regards to which big data analytics is used. And over there, we know that uh, the larger the data size we have, the better our models, AI models, can learn. So, and also there is this concept of frequent updates of the model. So if we have the capability to update the model on a regular basis, it certainly would lead to better accuracy of the AI models. Then there could be greedy algorithms and adaptive algorithms with regards to, or for implementing those kind of algorithms, we can use big data systems. Uh, Moving on to a very high level architecture of the different stages of the processing of data. So if we start from left, so we have the data sources. Then this architecture, it's called kind of a hybrid architecture. So there are two possibilities if we look at the top layer. So the first way is that we store the data as the data is produced from the data source. Then that data is processed in a batch format. As I mentioned, like for example, if we store data for collect data in a window of 1 day, and then we process that whole data. Then the data goes into some analytical data store, like we put the processed data in Cassandra or MongoDB or MySQL. And then based on our requirement, we just query the processed data to get the insight that we want out of the data. And finally, we present it to the user in the form of some kind of report, in the form of some kind of graphs, or depending upon the dashboard. And the middle layer shows that instead of the complete storage, we can ingest the data through a streaming engine for immediate processing or in real-time processing. So the data is collected and then directly it is streamed through a streaming engine, like for example, Kafka or RabbitMQ, into these big data analytical frameworks, which are used for processing like Hadoop, Spark, Flink. And same is the case when the data is processed, then it goes into the analytical store and finally reported. So in our group, the areas that we focus on, so the first area is big data analytical frameworks, which, as I mentioned, are used for batch processing or stream processing. So within the frameworks, primarily we work with three frameworks, which is Hadoop, Spark, and Flink. Then comes the data storage. So we also work in the area of data storage, and within that area, the key distributed databases that we use or research with include Cassandra, MongoDB, Redis, and MySQL. And the last one is about the data ingestion. So we also work with streaming engines like Kafka. So these will be the three areas that I would be focusing on in the rest of the presentation. So as I mentioned in our group or in the cluster of big data within our group, what we do is that we investigate, we develop, and we evaluate big data systems for real-time collection, storage, processing, and visualization of large-scale data. And within the big data systems, there are these three primary areas which we target. So it's storage, data ingestion, and analytics. And within the data analytics, we work both in the area of batch analytics as well as stream analytics. The application domains for what we target or what we have been primarily working on is the cybersecurity. We did some use cases in healthcare. We uh, worked in the area of oil and gas data with the oil and gas data, and for defense. So now focusing more on in one of the area that in the area of analytics, what are the key technologies, big data technologies that we use in our research group. So as I mentioned, that the frameworks that we use are Spark, Flink, and Hadoop. And just to mention again that these frameworks are used for the storage and for distributing the storage and processing of data on a cluster of computing nodes. Then we use different kind of languages, as these frameworks support different languages, like it supports Scala, Java, Python, and so on. In terms of languages, Spark and Flink, they offer much more flexibility. We have the choices. In Hadoop, we don't have much choice. It primarily supports writing applications in Java. Then we use HDFS as a kind of default storage with Spark, Flink, and Hadoop. We used different machine learning libraries that comes along with these frameworks, like Mahout, MLlib, and Flink ML. The key research problems that we look into are, we compare these analytical frameworks in terms of response time, energy consumption. Then another important angle that we look into is the configuration of these big data technologies, because It is not straightforward. On the other hand, it is not always that one configuration works or provides the most optimal performance. So in one of the project in the subsequent slides, I will show that configuration of the framework, it is an important factor. And in order to use these technologies to the maximum of their ability, we need to be very mindful of how we configure these technologies. And then also we look into some kind of trade-offs, that whether one framework offers one benefit at the cost of another. So like for example, Spark, it is better in terms of response time, but it is not that cheap as Hadoop, because Hadoop is a disk-based framework. So that is less costly, but at the same side, Hadoop is not as fast as Spark. So we also look into these trade-offs between different quality attributes offered by these analytical frameworks. The experimental framework that we use in our group, that how exactly we conduct experiments with respect to these big data technologies. So starting from the bottom layer, so in the hardware, at the hardware level, we use two types of clouds. One is the private cloud OpenStack, so that is installed here at the University of Adelaide. And then as a public cloud, we primarily use Microsoft Azure. We also use Raspberry Pis. We have high-end servers, which are more powerful computing machines, and we use laptops. For the connectivity between different kinds of clouds, like for example, connecting Azure to OpenStack, we use VPN. Mostly we use WireGuard. And then on the VM side, that what kind of VMs we use. So of course, we deploy some virtual machines in Azure, some in OpenStack, as well as we use Raspberry Pis. At the application level that I already mentioned, for the analytical frameworks, we use Flink, Spark, and Hadoop. And for the distributed databases, we use Mongo, Redis, Rike we previously used, but now it is no more available, so we don't use it. And we use MySQL. And the measurement probes, essentially, it mentions that what exactly we measure. So we measure bandwidth, we measure the energy consumption, response time, and so on. And the workloads we use, like whatever the benchmarking workloads are in the state of the art. So we use HighBench, we use Big Data Bench, and for distributed databases, we use YCSP. Key evaluation metrics. So these ones, just for the benefit of whosoever plans to work. So what are the key things that we can measure during our experiments? So obviously, one of the most important thing is response time, that how much time it takes to complete a particular data processing job, the scalability. Another very important aspect in terms of data analytics, because the load on big data system, it fluctuates. Like for example, a banking big data system, it would have more load at the end of a month where it has to process the salaries. Then probably similarly on a weekend, a system might have less load. And it's important that accordingly we scale the system so that we can reduce the cost, because if let's say we are using a public cloud and we are not able to scale accordingly, we would have to pay more without having any use of the resources. Similarly, reliability is another factor. For example, we need to be mindful that our computing machines, they are in good health. They are used to an optimal level. Energy, another important aspect, primarily if we are working in the edge. So we need to be mindful that how much energy our devices are using. Then CPU utilization, RAM utilization, disk and network. Those are other factors that primarily in terms of research, we need to justify our findings with regards to the uh, response time, scalability, reliability, and energy. This is now I'm discussing one of the project that we did in the area. So this was about the evaluation of big data analytical frameworks, and the primary questions we wanted to, and that we did with respect to different kind of clouds, like private cloud, public cloud, and hybrid cloud. So here, some of the questions that we answered through our work was that what is the impact of cloud bursting on the performance of big data analytical frameworks? So cloud bursting means that if we are running a data processing job on a private cloud and the workload it spiked, so in that case we have to offload some of the processing to the public cloud. Now when we do that, how does that essentially impacts our the performance of the entire system? Similarly, we did two type of scaling and we see how it impacts the performance. Like we added more cores, which is what we call vertical scaling to the same virtual machine. And in the horizontal scalability, we added more virtual machines, and we wanted to see that when we add more resources, how that essentially impacts the performance of the system. This is just a schematic of the infrastructure that we use. So on one side, we see OpenStack, which is a private cloud. On the other side, we see Microsoft Azure, which is a public cloud. They are connected through the WireGuard to run these experiments on. We used 5 different kind of workloads, which are from different domains, like knife bias k-means are from machine learning, grip, PageRank, and word count, they are from searching. Similarly, we try to use very much similar virtual machines on both private and public cloud for rather fair comparison. And what we found out from our experiments was that cloud bursting degrades the performance of Flink more significantly than Spark and then Hadoop. And also we found that within a hybrid cloud context, Hadoop Flink is around 30 times faster than Spark, which is around 15 times faster than Hadoop. In vertical scale up, we found that Flink is a framework that scales much better as compared to Spark and Hadoop. And then with regards to in comparison between vertical and horizontal scale up, so we found that horizontally these frameworks, they scale much better as compared to vertical scale up. In addition to while we were running this large scale experiment, we also found we learned some lessons that we thought that could also be useful for other researchers. So we also put them in our paper. So the first one is about the sensitivity of Spark to data size. So Spark, because it collects a lot of garbage, so as soon as we collect data size, if we keep the computational capacity the same, in some cases it can crash. So that is if anyone experimenting with Spark can keep an eye on. Then we found that Flink is a winner with respect to a couple of aspects. Like for example, with respect to response time, it is better than in most cases than Spark and certainly Hadoop. Another important aspect of Flink is that it is very easy to configure. Essentially, there is just one file that needs to be configured, while with Spark and Flink, there are multiple files that a user need to configure before running any application on them. Hadoop we found most consistent, so we run each experiment multiple times, and what we found is that Hadoop, it gives us more consistent values, while for Spark, primarily if we run the same experiment multiple times, the distribution of the points is quite high. And another thing is automation. So we recommend that anyone who is running these kind of experiments, they better need to automate the entire experimental process as much automated as possible through writing some scripts, because it requires the creation of the infrastructure, the deployment, then the destruction of the infrastructure on a very regular basis. So if someone is starting with a more manual way, it would be very kind of tedious and time consuming. And the last one is version compatibility. So these technologies, they keep on updating and versioning happens. So what we found is that at times one version is not compatible with another. Like for example, if we are using Hadoop with the high bench, so we need to make sure that high bench and big data in Hadoop, the versions that we are using, they are compatible, because at times what happens is that we start implementing, and then at a later stage, we find out that, okay, the versions are not compatible. So we need to make sure that before we start any kind of implementation, we make sure that the versions are compatible. This is another project that is primarily focused on the energy evaluation of these frameworks and making a comparison. So here the one aspect is that we don't look at the overall energy consumption. We only look at the energy consumption at the device that is offloading the particular task. So if we look at this figure, what we see is that the laptop, uh, it is under heavy load. And during that heavy load, what it does is that it offloads some of its processing to a cloud, like to OpenStack or to Azure or to a hybrid cloud. And what we want to see is that if we are running Hadoop on the platform or Spark or Flink, which one is more energy efficient and in which kind of scenario, because there are like 4 or 5 scenarios that are discussed in this, considered in this project. So some high level results shows us that the Hadoop, it is most consuming the largest amount of energy, then Spark and then Flink. And these results are understandable from the perspective of the response time of these frameworks. So since Hadoop is slow, what the laptop does is that when it offloads the processing to a cloud, it has to wait for the results. And during that process of waiting, it has to it consumes energy. So that is why it is slow. And also in this project, we considered that in which scenarios it is worth offloading and in which scenarios it is not worth offloading, depending upon the energy consumption. Another third project that we did was about the configuration of these analytical frameworks. So as I mentioned earlier, that each of these framework, they have like more than 100 configurable parameters. Like Spark has around 187 parameters. Now, not that all of them are extremely impactful, but some of them, as documented in the literature, they are like around 20 to 30 are very important and that need to be. And also importantly, the configuration varies from one workload to another. Like for example, if we are doing a machine learning task, we have to configure it in one way. But if we have to run a searching algorithm, we might have to configure it in another way. So in this project, what we tried to do was that first we tried to see the impact of this when we change the configuration, how much the performance changes. So in this figure, we can see that with respect to these different data sets like KD, DARPA, and this P1, P2, they denotes parameters. So we see a quite substantial fluctuation in the time. In the training time, we were probably training some machine learning model, I believe, naive Bayes here. So it shows that the right configuration, it is important in order to make these frameworks work in an optimal way. Here also from the scalability perspective, we see that the dotted lines present the ideal scalability, but these frameworks, as we increase the number of nodes in the cluster, they don't scale in a very ideal way. And that is another kind of thing that we considered in this project, the scalability angle. So here, if we see, we presented two different approaches for automated configuration. One we call scalar, another adapter, and scalar essentially searches for optimal configuration, and adapter, it follows some kind of rules to directly configure the framework before running any particular job. So each of them has some pros and cons. Like for example, scalar, it is more accurate, but it is slow because it takes time in searching. Adapter, it directly picks up the configuration, but so it is fast, but it is not that accurate. In the area of big data storage, we, as I mentioned, that we work primarily with four. We used to work with 6 databases, but because one like Rike, it becomes unavailable due to some issue at the company that was offering the this database. And so currently we are working with Cassandra, MongoDB, MySQL, and Redis. And here the questions that we mainly look at are that when should we offload big data storage tasks to a cloud? So we essentially try to have these databases running on at one end, like a laptop or a high-end server or a Raspberry Pi. And then we see that, okay, what is the point where we need to offload to a cloud? And then which storage solutions are highly energy efficient? So we looked into their response time, that, okay, if I'm performing a query on reading some data from Cassandra or reading some data from MongoDB, how that differs, and also which one is more and less energy efficient. And another angle is the cloud busting, as we considered for the analytical framework, so does we consider for the databases, that when we upload from a private cloud, when we upload processing from a private cloud to a public cloud, how that exactly impacts our the performance of these databases. And similarly, another angle that we consider is the scalability, that whether they scale better horizontally or they scale better vertically. Now moving on to out of our research projects, I'll talk about the trends in big data, that what we should keep an eye on in future if we are working in the area of big data analytics. So the first one is the coexistence of public and private cloud. So currently, as we see, enterprises, they either are using private cloud or using public cloud. So in future, we would see more and more a hybrid approach where enterprises would prefer to use private cloud, and then under spiking workload, there will be a connection and they can upload to a public cloud. So the advantage is that they can, from the security perspective, they can analyze the sensitive data on private premises, and the one that is non-sensitive, they can upload it to a public cloud. It will also reduce the cost, because if we are not using public cloud unnecessarily, rather we only use it when there is a spiking workload, so it will reduce the cost. Another angle is about the big data and DevOps. So we would see a competition, because big data, the competition to collect and analyze more and more data is on the rise. And what we hope to see is that the uh, organizations will compete to offer quick big data services. And for that one, the evolution angle becomes very important, that their big data systems are able to evolve as the customer's needs evolve. And for that kind of evolution of software systems, there is a need of continuous engineering. So the organizations having the ability to cope with the changes, incorporate new big data technologies would have some kind of edge. The third one is about the sharper focus on data governance. So uh, because this kind of thirst for more and more, collecting more and more data and analyzing data, it also has the side of whether it increases the risk of misusing the data. So there would be more stricter governance models, that okay, how the data should be collected, how it should be analyzed, and to whom the findings can be shared. Seeing future for IoT and big data. So IoT, it is becoming more and more pervasive, and as IoT is the adoption is increasing, it would lead to generating more data. And with that data, we can see far more use cases for the application of big data analytics. Then is the user-friendly big data services. So currently, one of the issue that we see is that these big data technologies, they are not very straightforward to use. So essentially, the installation, the configuration, it requires some bit of in-depth knowledge. And because of that reason, not many people are able to use these big data technologies. So one of the trend we can foresee is that uh, big data would be offered as a service, where people can just submit their requirements in very plain text, and those requirements would be automatically converted into a service that would be offered to the user. In data preparation, so what we normally hear is that around 80% of the time of the data science engineers, they spend on cleaning the data, and at the same time it is the least interesting thing to do. So we could see more and more technologies coming that can automate the process of cleaning the data, like for example removing the outliers or filling the missing values and things. More concretely on what we intend to do in the near future is we try to answer some of these research questions. The first one is about that what are the pros and cons of the big data services offered by various cloud providers. So these public cloud providers like Microsoft, Google, Amazon, they offer different kind of big data services, like Microsoft offer HD Insight. So we want to compare that what are the pros and cons. Like for example, one may be cheap, another may be faster, another might be more scalable. So that kind of comparison would be very insightful for the users, that okay, according to that to their needs, they can choose a particular provider. Then is the impact of distance. So for example, the clouds that are we connect like private cloud and public cloud. So if there is a bigger distance, like for example, the private cloud is located in Adelaide and the public cloud is in Sydney, or in comparison, the public cloud is in United States. So how does the distance impact the performance? Because distance has a relationship with the latency. So that would be another thing that would be worth looking into. The third one is about the distributed databases that now are essentially most of the research that I have read, that people use these frameworks for default data storage, what is called Hadoop distributed file system. So it would be worth looking into that if we use Hadoop with Cassandra and if we use it with Mongo, which one offers us the best performance? Similarly, correlating Spark or connecting Spark with Cassandra, Mongo, which one is the best one for Spark? And along the same lines, the correlation between streaming engine and analytical framework would be worth looking into, that if we use Kafka with Hadoop and Kafka with Spark, which one offers us the best performance? Or if we use RabbitMQ with Hadoop and Spark, which one offers us the better performance? So those are some of the concrete areas that we plan to look into in future. These are some of the publications we have in the area of big data analytics. Thank you for listening, and if you have any questions or comments.
Yeah, thank you. Thank you for your great presentation, Faheem. And yeah, exactly. We now would like to open our Q&A session for the question for Faheem. I just wondering, Faheem, what are the another hot topics in your new research area? Could you give us some your thoughts on this?
Thank you, Anita, for the question. So in this slide, some of the topics that, in my view, are kind of worth looking into is like if we could see the incorporation of, like for example, the DevOps and big data systems, that how much benefit it can give us and how much evolution or rapid evolution we can see in the area of big data systems when we continuously engineer it. And another is that, for example, in IoT, we can bring more and more big data analytics. We can push the data analytics towards the edge. And that could be, I think, something worth looking into in future.
Yeah, very interesting. Thank you, Faheem. Do we have another question in this round? If not, I'm pretty sure Faheem is available for question via email or in person at the uni. And yeah, I would like to thank you, Faheem, for your great presentation again, and thank you all participants. And I wish you a great day. Bye.
Thank you, Anita. Yeah,
Bye.